Welcome, everybody. First of all, I want to apologize for there was a misstatement in the alert, and hopefully we got that corrected by the signs in the elevators. And so we wanted you to be able to see the building of the James Webb Telescope because a lot of the information that is generated by that incredible feat is going to be the subject of our talk, both here and perhaps in future sessions. And we will be recording this and as well as the video, and so we'll be able to replay it for those people who cannot attend. Our speaker today is Dr. Bruce Balick. He's a professor and former professor emeritus and former chair of the Department of Astronomy at the University of Washington. He's a graduate of Beloit College and received his doctorate in astrophysics from Cornell University. He has an international reputation for his expertise in the study of planetary nebulae, the celestial remnants of sun-like stars and their final stages of evolution. And he played a major role in the discovery of Sagittarius A, the massive black hole at the center of the Milky Way galaxy. He has collaborated and co-authored research papers with Joel Kastner, whom you all know, and whose mother lives among us. And he has spoken several times in a series of astrophysics and astronomical topics here. Joel has as well. Even though he's retired, Professor Balick continues to contribute to published research based on data from the Hubble and the James Webb Space Telescope. The development and launch of the latter was just described in the video you saw. One might think that such research must be fairly esoteric and abstract, but I was intrigued by some of the titles of Dr. Balick's published works. For example, The Tempestuous Life of the Butterfly Nebulae,
with Joel,
The Messy Death of a Multiple Star System and the Resulting Planetary Nebulae, and Excitation and Excavation of the Claws of the Southern Crab. Who knew such scandalous things were going on in our universe? Please welcome Professor Bruce Balick.
thank you. And a great introduction. And I have to mention, well, a few things. I'm going to change this talk. Originally, I came here prepared with a talk, half of which is the building of the Webb telescope. Louder? Okay. Is that okay? Okay. The first half of the talk I came here prepared to give is on the building of the telescope. The movie completely upstaged me. If you didn't see it, I really, really recommend it because a lot of NASA's known for its hyperbole, but there wasn't any in that movie. The excitement of all of us on the launch and the successful deployment of Webb had us enthralled for 6 months. Every morning I would wake up and go to NASA TV to find out what was new, changes in status. If you saw the movie, you heard that there were 344 single-point failures starting at launch. So what that means is there are 344 steps in the deployment of the telescope, and if any one of them doesn't work, that's the end of life. So it was a cliffhanger for all of them. And these were not easy steps. These were amazingly difficult steps, and all of them were accomplished after launch. Once the telescope is disconnected from anything that humans can touch, on its way out to where it will live, is living, 1 million miles from the Earth. So the moon is a mere 250,000 miles away, and James Webb is 3 times further than that. The movie did a wonderful job at answering the question, why stick a telescope out there that we can't repair, as we did Hubble on many occasions? What is the point of going that far? And I'll cover that and many other things as I get into the talk. But I just wanted to give you a sense of my personal thrill at the deployment of the Webb telescope, and to let you know that Joel and I have been collaborating for the last 3 or 4 years, at first on Hubble data, but now on just spectacular data from the James Webb telescope. So these telescopes have meant a lot to me, and I'll say more about that. And Jack told me that I could skip, for now, the presentation of the new results from Webb, which are really exciting, really exciting. I'll come back, we'll arrange a time, and I'll do it. It's a pleasure to be here. It's a pleasure to be with you. You, among other things, have made my career a success by paying your taxes. Your taxes paid for Hubble, they paid for Webb, and they paid my salary at the University of Washington. And I will say right here and now that my career at the University of Washington was just absolutely wonderful. The opportunities to work with students, the support of the administration for the department and getting us resources, the infrastructure that the university provides are things that for which I'm very, very grateful. And I decided on retirement to repay you, at least in a small amount, for your support by coming to give talks like this. I've given 3 talks at Skyline. This is my first talk here. I love these things. So I have talks on, right after this, my wife and I get in the car, and we drive over to Winthrop, where our 2 granddaughters live, and on Monday, I'm going to be giving talks to both of their classes on aliens. It is such a fun topic. And I also have talks prepared on the origin of the universe, the Big Bang. All of those questions that people like to ask is like, what's beyond the edge of the universe? These are fun talks to give, so I'd be delighted to be invited to come back. But we definitely have a date to review the latest images from Webb and their impact on science. All right, so let's get started. I hate to say, I'm no Albert Einstein, but that he is me and Joel and everybody who's in astronomy. It's just let me give you an example of why it's so exciting to be in astronomy. I came to UW in 1975, and one of the first classes I taught was an introductory class. And the way these introductory astronomy courses go, you go through planets and then stars and then galaxies and then cosmology, like the origin of the universe and so forth. In 1975, as the course ended, I would cover the topic of how old is the universe. All that we knew in 1975 was that it was older than the oldest star, 12 billion years, and it was younger than the Hubble law. This would take too long to describe, but from the Hubble law and the rate at which objects move away from us as a function of their distance, we can age date the universe from that. In 1975, the universe was somewhere between 12 and 16 billion years old. Now, catch this. We now know the age of the universe, 13.77 billion years, to better than 1%. That was unthinkable in 1975. It was a lot of work to get that done. It was not an easy experiment, but that's where we are. The field changes so fast that if you teach Astronomy 101, you have to prepare fresh lectures almost every year that you teach it. It's a thrill to be in a subject like that, in which the frontiers of our understanding are breaking open all the time. There's always a surprise. Certainly, the project that Joel and I now are working on Webb data, just floored both of us. If I had time, I'd find his email to me of 2 days ago saying, gee, the images that I put together in a mosaic are just astounding. And he goes on to say, they're so complicated that it's unlikely that we'll ever understand the origin of what we're looking at. All right, that's the way it goes. And I'm sure people will be eating those words. I will be eating those words if I'm still alive 50 years from now. But it's wonderful. Okay, so astronomy is going through amazing changes, largely the result of big new telescopes that reveal things that we could not have imagined. It's the telescopes which provide these peeks into the strange behaviors of the universe, which drive the field forwards. When I get data from Hubble, I get an email one day, and as you apply for time in Hubble, 1 out of 8 proposals gets it gets any time at all. You never know when the observations are going to be made. They're made at the convenience of the telescope. They're trying to save the gas that steers the telescope as long as they can. So they schedule the observations as a matter of convenience. But when you get them, this email says, go look in the archives, your data are there. And it is such a thrill to go into the Hubble archives and to find these new images. And you just revel at what you see. It's just, it's all these devils are in the details, and that means after 5 minutes of absolute elation comes this dawning realization that they didn't give you time on the Hubble because they like you. You are obliged to figure out what the basic questions, the reason. I mean, you apply for time to explore something for which we don't know the answer, and the data have to be used towards that end. And it can be so intimidating to realize that these stunning pictures, I have to make up a story to go with them and make it accurate and make it based on evidence. That's the real thrill of doing the science in general, right? So I'm spending too long. We are very fortunate to have a whole set of new telescopes. Can you see this pointer? This is a brand new radio telescope in the high Andes in Chile, up at 15,000 feet. It's in Chile, but right on the Bolivian border at the crest of the Andes. I've been at the bottom of the mountains. They won't let you up to the top because it's 15,000 feet. And at my age, they worry that I'm going to have oxygen starvation. Joel is leading a huge project on the same thing we're working on at Webb. That's a different story. This is the Vera Rubin telescope. It was supposed to go into operation in 2023. It'll be 2 years late. The University of Washington is one of 4 founding partners in this project. Inside the dome here is an 8-meter telescope, one of the largest in the world. But this 8-meter telescope is designed for one purpose, unlike all the others. It's going to survey the whole sky at great sensitivity every 3 days. This is the way we're going to find abrupt changes in starlight or supernovae or explosions or even asteroids that are crossing the field. And you don't apply for time on this telescope. The telescope runs routinely on its own. The data become open to the public the morning after. So everybody on the surface of the planet will be able to see the latest set of pictures. For the most part, they're going to look exactly like the previous set. And so there's a pipeline built into the data flow from the telescope that asks what has changed. That is, you look at a patch of sky every 3 days for the lifetime of the telescope, 10 years, right? And what you do is compare each of the images to the others to see what wasn't there before. This is going to, we've been working on this for 10 years. There are small telescopes that survey the whole sky. We have discovered all kinds of things that flash, right? Most people think the sky is always the same. It isn't, and learning why is really exciting. All kinds of new types of objects have been identified. Objects that emit a burst of gamma rays, which are light, which is so energetic. It's more energetic than X-rays. So X-rays, as you know, go right through you. And gamma rays are 10 times, 100 times more energetic than X-rays. And anything that in the sky that can emit light of that energy is really exciting, really exciting. Anyway, there are piles and piles of new telescopes. Webb is certainly, for now at least, leading the way, like Hubble did before. I'll come back to that in a little more detail later. First, let's talk about how telescopes work and what they do. Their only purpose is to collect faint light and image it, focus it onto a camera, right? So they collect light just like an umbrella does. The bigger so this, I have a pointer. I have to remember to use it. This telescope here collects more rain than that one down there. Bigger is better. Bigger is better. There's no substitute for big. The light that comes down from the sky is coming down as little particles of light, right? Just like they're the same particles that are coming. They're not really particles, but they're localized regions of light energy that travel as a wave. But for our purposes, just think of them as marbles coming down from heaven, bouncing off the curved surface of the mirror and being focused to a place at the top where we can do something with them. Now, all telescopes work this way. Radio telescopes, X-ray telescopes, infrared, they all work this way. There are some differences, and I'll begin to mention them here. Here's a cartoon of the Webb telescope. Light comes in from the left, but in this picture, the light rays are diverging. They're not. The light source is so far away that the particle streams are all parallel. That doesn't matter much. They bounce off a curved mirror, the primary mirror, in this case, made of 18 segments all pushed together and aligned very carefully to make a single image. In the movie, we saw that at first, the first pictures taken of a bright star had 18 bright stars in it because the mirror segments hadn't quite been aligned yet. That was one of the trickiest parts of the deployment of Hubble, and it just went perfectly. NASA had given itself 6 months to do the alignment, and they did it in less than 2. Anyway, in this case, the light comes to a second curved mirror at the top. From here, it's directed into a hole through the center of the primary mirror, into the back here, where lots of scientific instruments are located, and the light can be diverted into any one of those. I think there's a small mirror, just like your dentist uses to look in your mouth, at 45-degree angle, and it sends the light coming in this way to any of the instruments that are located back here, of which there are 4 principal instruments. So right now we're talking about light, not about the details of Webb and how telescopes work. So bigger is better. The power of a telescope is measured by the rate at which it collects light. So
1/4.
Well, actually by the size of its aperture. The human eye is about a centimeter. You're all familiar with that. Hubble is 240 centimeters, 94 inches, so it's much bigger than your eye. And it has the light gathering power of about 60,000 of your eyes. And Webb is bigger still, so it collects almost 500,000 times more light than your eye does. And there are much larger telescopes. The 8-meter telescopes have a gathering power of well over 1 million eyes. And this is why astronomy moves forward, because the bright things we've been studying for years because they're easy. The science is in the things that are difficult to observe because they're faint. Now, one question you should be asking yourself is why to go to all this expense and engineering trouble to go up into space? And the answer is photons from far away travel nicely from their source for many light years. A light year is how far light travels in 1 year. And we're looking at things that may be as much as 13 billion light years away. They're faint. They may be very bright if you stand next to them, they are. But by the time we gather the light, it's very, very faint. Anyway, those photons come in from space, and at the very last instant, they go through the Earth's atmosphere. And that atmosphere is like the waves on the top of a swimming pool. If you're inside the swimming pool and you look at trees through the top, the ripples on the surface just blur the image terribly and make it wander around. We go into space to avoid that. That is the principal reason. There are some other reasons too. The Earth's atmosphere absorbs some of the light that comes down. Right? So hard ultraviolet light gives you cancer, and our atmosphere protects us from that. But if you want to study ultraviolet astronomy, you want to be up there, not down here. The same is true for infrared, for X-rays. You have to go into space. So on the left is an image of an object, a planetary nebula, the objects that Joel and I study. The one on the left was taken by students of mine using the University of Washington 140-inch telescope in New Mexico under conditions of exquisite atmospheric stability. Hubble took the one on the right. And there's a world of difference in terms of the science between these two images. So we were at a meeting at Innsbruck. The topic was planetary nebula. It was a research meeting organized for international astronomers who work in that field. It was in 1994, and if you saw the Hubble, the movie just before, you know that at first, Hubble was way out of focus. The reason was deeply embarrassing. NASA had paid a fortune to figure the primary mirror perfectly, and it was figured perfectly, but to the wrong curvature. And there was no way for Hubble to be focused to make the images as clear as this one. By 1994, the astronauts had gone up and replaced all the instruments with new ones that had a little tiny contact lens at the front of them. And the contact lens corrected for the vision of the primary mirror. And at this meeting in 1994, the picture on the right was released by NASA as we were having afternoon coffee at the meeting. And my colleagues and I looked at each other with again this look of a deer in the headlights, right? What the hell goes on to make the object this complicated? It was never expected. So now we know the answer, and that would be the subject of the future talk. But the point is, as I mentioned before, these exquisite new observations can really upset long-standing beliefs and a lot of work done in science, and that's exactly why we put them up there. The clearer the image, the more you're going to learn. So briefly, here's Hubble being deployed from the back of the shuttle. The size of Hubble is the size of its mirror. The most critical part of the whole telescope is determined by the width of the cargo bay on the shuttle. We could have made a bigger mirror, but we'd have no way to get it up. Now, in the case of Webb, the mirror is 2.5 times larger in diameter than Hubble, and it could not have been deployed by the shuttle, but by that time the shuttle program was over. The only way to get it into space was this huge European rocket known as the Ariane, which has now been discontinued. The Ariane had the lift capacity and the size to get Webb into orbit, and Webb was designed to fit in the nose cone of it. I worked on the Hubble for 11 years. I was part of a design team building a second-generation imaging camera. The first-generation imaging cameras, the one with the little contact lenses, were wearing out, and there was new technology. We really wanted to get that new technology into orbit. So I was part of a design team to put in the newest imaging camera, which you see right here. I want to tell you a short story about that. It's a fun story. This went up in 2009. At the time, I was chair of the UW Faculty Senate. I was required to attend all the regents' meetings and give reports about the status of the faculty in the Senate. Fine, but the day this camera was put in the telescope coincided with the meeting of the regents. I had just come back from Cape Canaveral. We had been funded by NASA to go down and see our instrument launched. It was a very exciting time. And I was, all pumped up. I have to go to this regents meeting and sit through all the financial reports, blah, 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 blah. I'm bored. The astronauts are putting this camera in the telescope at the time of the meeting. It didn't go well. I'm sitting in the back of the room with my laptop and earphones and watching all this. They couldn't get the old camera out. Right, the new one has to replace an old one. And there was one bolt that held the old camera into place, and it wouldn't break loose. The astronauts went up with a wrench, wouldn't budge. They went up with a special wrench, a torque wrench, which is calibrated, and they were told how much torque they could exert on the bolt. If they exceeded that, it might break. So they go up with that wrench, put it on, nothing. So they go down and get the big wrench, right, because there's not much to lose here. NASA tells them the bolt that's holding the old telescope in has 22 threads, right? And so I'm in the regents meeting. The announcer is counting for us the number of turns, right? And I must have been repeating that because when they got to 22 and the bolt came loose, I must have said something because all heads in the regents meeting snapped around, and the president of the university during a break said, "What the hell was all that about?" And I told him, and he told me I had to talk to the regents and explain what was going on. It's an experience you don't forget that quickly. This is an example of a Hubble image of special interest to me. The Hubble data comes from a project in which Joel was the lead author. When I retired in 2014, I said to myself, that's it. I'm not writing another proposal. Each one of them takes weeks to put together. The chances of them getting time on a Hubble are 1 in 8. I got better things to do with my time in retirement. Joel was kind enough to add me to the team. And this is an example of the images that we were working on. This object, known as the Butterfly Nebula. It was supposed to be a nice, simple nebula, looking like a butterfly. And if you take its picture from the ground, that's what it looks like. But look at all the structure in here. We found as a result of our work on the images that this blue region is a region through which fast gas, a column of really high-speed gas, like that coming out of the back end of a jet engine, was flowing this way at 700 kilometers a second, 400 or 500 miles per second. We'd never seen anything like that anywhere in an object of this type. And there were other flows like these that had speeds of up to 300 miles per second. And there was one that's off the edge of the photo of the image here at 800 kilometers a second. All of these things are ultimately powered by energy from the star at the center, which is dying. It's going through gasps, right? It's coughing as the last of its fuel sputters. It's like a car running out of gasoline, and it sort of jerks as it ends up. And that's what this star is doing. The point is to figure out how and why, and we still haven't answered that. These results just blew us away, and there's no known mechanism to account for all that. This is the same object that we're now observing with Webb. Right down here, there's a dust lane in this picture that blocks our view of that star. So the Hubble images, until you observe the star, you don't really know what's going on. And infrared light, the long wavelength infrared light is able to get through the dust, and on Webb for the first time we're able to see the star. Turns out it's wrapped up in its own cocoon of dust, so we can't actually see the star, we can only see the cocoon. But it's by observing and finding out what the star does to its surroundings that we will eventually understand how that star works. All right, enter the Webb telescope. If you saw the movie, you saw this launch. There were a lot of you that didn't see the movie. It was on Christmas Day in 2021. Like every astronomer in the world, I'm glued to my television set, NASA TV, and we're mentally counting down with the control crew, and fingers are crossed. I mean, as the movie shows, getting Webb to the launch site involved 15 years more of work than were planned for at the outset. The budget had gone from $1 to $10 billion. There were all kinds of hitches in the history of Webb's design. It was just amazing that NASA continued to, Congress continued to approve the appropriations needed to get this thing to the point where it could be launched. It's not a story of mismanagement. Well, there's some mismanagement in that. It's really a story of this gigantic telescope, 7 tons of it, with all kinds of things inside that I'll show you in just a minute, each one of which has to work perfectly. It's the complexity of the telescope which led to the delay in its launch. There was no fundamental management problem. Management was just being surprised all the time that the technology that they thought was going to work didn't work. And of course, they're using state-of-the-art technology, so there's a lot of risk that goes along with that. But anyway, on Christmas Day, we're watching television, just thinking about this $10 billion telescope wrapped up in this gigantic rocket, which will be launched at incredible acceleration that's going to shake the hell out of the telescope. A very delicate instrument with millions of working pieces, all of which have to have a job to do before the telescope works. It's a cliffhanger. The deployment I mean, the launch was perfect, absolutely perfect. On NASA TV, they were counting down from the 344 single-point failures. As they got past each one, the count would go down a little bit. Every astronomer, of course, is watching this. 33 minutes after launch, the telescope comes out of the nose cone and heads off into outer space. It's headed to a point 1 million miles away, which is a very, very special point. It's at the point where the gravitational tug of the Earth and the gravitational tug of the Sun are in delicate balance. So the telescope is like a marble on the top of a peaked hill. Anything wrong, and it will either fall into the Sun or fall into the Earth. This launch has to be perfect, absolutely perfect. Now, nothing's ever perfect. So the telescope has gas inside that it uses to make little jets that correct the trajectory. And that's the same gas that will guide the telescope to different stars when it goes into operation. All right, so the estimate was that half of that gas would be used up getting Webb out to where it had to be, and the rest would be available for science. And the lifetime of the telescope would be determined by how much gas was left when the telescope reached orbit. The good news was only 20% of that gas was used getting the telescope to where it had to be. So the lifetime of Webb went from a rough estimate of 10 years up to 30. Yay! I mean, our graduate students will still be using Webb. This was really, this is the last picture basically that we got. There are a few more pictures that showed up in the movie, but this is the last still that I could get hold of, and it's free. Now, there's a long road to hoe, right? There's this telescope, which has been packaged into this tiny little thing to fit in the nose cone, has to unfurl. It's very complicated, and there are many steps, including the sunshade, which I'll show to you in just a second here. But first, here's a picture showing where Webb is, where the moon is. The movie makes the point properly, and many times, that we will never go to Webb to fix it. It has to work all on its own. So it's set up with a lot of redundant systems just in case something fails, right? And so far, everything is working perfectly. These are some of the steps that the telescope took during its trajectory to where it is. So the trajectory is illustrated here. The telescope has to gently settle into that critical point, otherwise it falls to the Sun or to the Earth. But during the ride, the solar panels come out. The telescope can only last for a few days without fresh power in its batteries. Everything worked perfectly. This shows this thing called a sun shield. You can see it here. It's made out of 5 layers of stuff like mylar, potato chip bags, that protect the telescope from the heat of the sun and the Earth and other sources. The telescope is designed to be an infrared telescope so that it can explore the events in the early history of the universe, 13 billion light years away, and the light from objects out there is shifted by the expansion of the universe until it's in the infrared. It's very difficult using optical telescopes like Hubble to see things out there. Webb was designed, among other things, to explore the very first stars, the first generation of stars, which it has been doing successfully since its deployment. It's really, there are many surprises, as you might expect, and I'll leave that topic for a future talk. But the shield, the heat shield, is a vital element in the operation of the telescope. 5 layers of mylar, they have to be unwrapped, separated by a few inches, or the heat from the sun will destroy the detectors inside the telescope. And the way this works is that the heat shield, that gas in the telescope, it orients the telescope so that the heat shield always puts the telescope in the shadowed side. Right, so this thing is going around the Earth, just like the moon has one face at us. That means every orbit it has to turn exactly once in order to get back to where it begins. During the orbit of the telescope, the heat shield and the telescope assembly have to rotate exactly once, so that the sun is always shaded. In principle, it's very simple. The heat shield deployed perfectly. The telescope itself, most of the segments were packed inside the telescope. The outer segments wouldn't quite fit, so they were put on flaps with motors that would bring them into position at the last minute. That worked perfectly. Everything worked. Everything worked. This is really an unbelievable engineering success. Let's briefly talk about Webb's prime mission. Yeah, I'm running out of time, which is fine. The prime mission of Webb is to look back through time to explore the first generations of stars. So this shows sort of a cutout of the entire universe. It's the space through which Webb looks. So here's this slide. It shows Hubble instead of Webb. It doesn't make any difference. These are the objects near us now. They're not all that far away, but because the universe expands, they're all moving away from us. And the rate at which they move away from us, the rate at which their visible light of the stars shifts from the optical part of the spectrum into the infrared, all that increases with distance. So as we look back through space, and because light travels so slowly, as the movie pointed out, you weren't all at the movie. Sidebar, the sun is 8 light minutes from the Earth. When we look at the sun now, we see it as it was at the time that it emitted its light 8 minutes ago. What's the sun like now? Wait 8 minutes. It's the only way to find out. The nearest stars are about 4 light years. The nearest star is about 4.25 light years away. We see it as it was when it emitted the light 4 years ago. This continues. The nearest large galaxy is the Andromeda galaxy. It's 2 million light years away. When we view it now, we view it in a state when it was 2 million years younger. Keep going. The objects that we see at greater distances, and they're becoming fainter with distance, the objects that we see are younger and younger if you measure them in time from the birth from the Big Bang. So we look back here and we see a younger and younger universe. We see our own cosmic history thanks to telescopes like Webb. No historian at the University of Washington or anywhere else has a tool to see history in the way that we do. We are so lucky that light travels slowly. But we're getting this wonderful picture of the evolution of our universe as we look back and back into time. Now, Hubble and Webb are looking at starlight. Somewhere out in here, when you get back far enough, there weren't any stars yet. The universe was too hot, much too hot, right? Like boiling water, or even worse. It wasn't until the universe had aged for 300,000 years that it became transparent, right? So this room was transparent until you hit the walls. And the universe is transparent from here back to 300,000 years after the Big Bang. And then you hit a wall like that, and you can't see through it. Or you can't see through it, but you can see structure. I see the grain of wood back in there. And from that structure, I can make inferences about how that structure got there from earlier events. So that's a different talk. But as we go back, after about 100 million years from the Big Bang, the universe had cooled and settled enough that the first stars could aggregate gravitationally without being dissolved by heat. Right, we can see those stars, we can see their light, and we can explore the structure of the universe at a long, long time in our history, cosmic history. And we can also look at what happens, how stars form in that era. Star formation is basically gravity pulling things together, but the details really depend on how the guts of the star can cool. And the cooling process is the process by which light is thrown out into space, carrying energy away from the hot parts. And in the early today, there are a lot of elements around which weren't there at the beginning of time. Right? When the first stars formed, the universe was only hydrogen and helium, and they don't emit the kind of light that really cools stars very effectively. So the process of star formation is different as the universe ages. We are very lucky to, well, no, sorry, it's not a matter of luck. The gold that's in your necklace, the carbon that gives you life, your DNA, none of those elements were here at the beginning of the universe. It was too hot. If you made a nucleus like that, the heat of the early universe would just knock it apart. The nucleus would dissolve almost instantly. The formation of carbon, calcium, gold, and iron, and everything else happens much later in the history of the universe, when these elements are made inside stars, in the guts of stars, and then the stars explode and send all that stuff out into space. What we can now do is look at the star formation when these heavy elements which cool the star and allow it to collapse. We can look at that process now directly, because our theories of star formation without the heavy elements are not very realistic. Anyway, this is Webb's prime mission. We already knew from Hubble that as we looked further and further away, the galaxies that Hubble could see were getting smaller and fainter, as you would expect, but their shapes were also different. Here's a Hubble image of the most distant galaxy that it could ever see, and it's just kind of a red smudge. As you go this way, you see galaxies in different stages of their formation. Today, most of them look like this, or sort of soft blobs of light, of stars. One of the big goals of science is to understand where we come from, and that's a matter of understanding how planets form, which is a matter of understanding how stars form, which is a matter of understanding how galaxies form. We have a huge group in the University of Washington who studies galaxy formation. They do it through a combination of theoretical simulations and optical images. Oop. Webb can see, because the light from the distant objects has been shifted out of the optical portion of the spectrum into the infrared, we designed Webb to be an infrared telescope so that we could observe these things. It's a huge infrared telescope. The Earth's atmosphere absorbs almost all of the infrared. So Webb is not only useful for that purpose, but for a number of other purposes that involve the observation of infrared light, which we can't do from the ground, but which we can do from space. So Webb is extending our understanding of black holes, star formation in general. It's been used to look at the planets. I'm going to talk about all that next time and give you the latest results. But one of the first images taken by Webb is shown on the right. NASA picked what appeared to be the darkest patch of sky, right, and just pointed the Hubble telescope into it for 11 straight days, taking a long exposure, and this is what you see. In a few hours, Webb took this image of the same patch of sky. These galaxies here are those there. And suddenly we were looking much further into the depths of time than we ever had before. This was thrilling. This was really thrilling. None of us knew exactly what to expect because our theoretical understanding is not all that great. In fact, one of the reasons for building Webb is to improve our theoretical understanding. Oh yeah. So it's these little tiny dots here, the tiniest, faintest dots, which are the oldest and furthest objects, and they're the things we're trying to study. And I love this quote from Winston Churchill's father, who was the Treasury Secretary in Britain in the late 1860s or 70s. It was his job to balance the books every year, and he couldn't do it, right? And he didn't understand decimals. So at some point he muttered this. And that's what we're trying to do with Hubble. This illustrates the reach of telescopes in terms of depth into space over the course of time. So in 1990, the largest telescope was the 200-inch telescope at Palomar. We were just leaving the era of photographic plates, which aren't sensitive, and entering the era of the technology that's in your cell phone to take pictures. Right, digital light detection. And this is as far as we could go, about 6 billion years back in the history of the universe. Hubble, at first, pushed that to 1.5 billion years, but after its cameras were updated, it got out much further. Hubble's best effort is this one in 2010, using that camera that I had worked on for so many years. And it could get back to about 500 million years after the Big Bang. Webb, already in 2022, with only a 12-hour observation, was reaching to 200 million years. And in fact, some of the newer data that I will present in a future talk allows us to look at stars, galaxies, just a mere 100 million years after the universe is born. 100 million years. The universe is in its infancy. It's 13.8 billion years old now. And 100 million years is I can't do the math in my head, but it's roughly 10,000 times. What am I trying to say here? I'm having a senior moment. You guys know what those are. The kids in the classes will never understand. Anyway, we're going to push on here. I'm not going to waste your time. On July 11th, 2022, the mirrors had been put into alignment. And so the crew that ran Webb changed from the engineering crew over to a science crew. And just before July, the first images, science quality images, were taken. One of them, this one, is of an object of the sort that Joel and I and other people study, known as a planetary nebula. The word planet is a complete misnomer. William Herschel was the first person to find a planetary nebula, and he said, oh yeah, it's kind of round and fuzzy, reminds me of Uranus. So we called it a planetary nebula. Planetary nebulae are strewn throughout the universe in galaxies. Our galaxy is about 500,000 light years across. Most of these things are very far away. This one happens to be just a mere 3,000 light years from us. And the closer they are, the easier they are to study. And so this was one of the early release images. I got a call from a reporter. I'm just about to finish. I got a call from a reporter from the New York Times about a week before this. That reporter had been told by NASA not the names of the objects that would be, whose images would be released at first, but the types of objects. So the reporter knew that a planetary nebula would be featured in this early release image set, which came out on July 12th. You never know exactly when NASA's going to release the embargo on the data, and people can get a first look. I got up very early this morning, turned on my computer, waiting to see what would happen. The reporter said that as soon as the image is released, he was going to call and ask for a quote from me. Wonderful. But that morning I had a dentist appointment. So I walked from my house to the dentist across the campus. My phone is out, and I'm waiting for this image to show up. Nothing happens until the instant that I climb into the dentist's chair. And then my phone rings, and by that time there are things inside my mouth. And the reporter wanted a quote, and I had concocted one just for this event based on a word that I had never been able to use in a press release, but I was going to use it now. And I said to the reporter, with all these things hanging out of my mouth, I said, "I'm gobsmacked." That was the quote of the day from the New York Times. So on that note, I'm going to pause here until I come back, and I thank you very much for your polite attention. I can't stay long because my youngest granddaughter is in a play tonight all the way over in Winthrop, and we have to drive over there. So I'm going to run like hell to get out of here. But there is time for a few questions.
We do have time for a few questions.
I wear hearing aids, so speak clearly.
Yeah, I have a question, or more a comment. I can't imagine a light day.
There you are.
We're dealing with information that we know yet cannot comprehend. The dimensions that you cite for the universe are impossible for the human brain to wrap around.
No, they're not.
Beyond my imagination.
It takes experience.
Well, it must take a good bit. I can't wrap my mind around them. I thank you for your talk. I wish we knew what was beyond that billion light years.
Well, that's a future talk. And the answer is nothing. Well, no, that's not true. The answer is more of the same. But there just hasn't been time for that stuff beyond the visible age of the universe. There hasn't been time for its light to get here. So we just have to, if you want to know the answer to that, just wait a few million or billion years and its light will get here. But we think it'll be the same sort of thing that we see right here at home.
When you showed the photo of the butterfly nebula,
Yeah.
it was the color that attracted all of us. Will you comment on the color? Because I
will.
understand it's not really there.
All right. You're absolutely right. I mean, Photoshop puts it in. So when you get images, either from Hubble or from Webb, they're pictures taken through a single filter, and the image is a black and white image. If you take multiple images of the same object, you can put them into Photoshop and show them in different colors. And that's exactly, that's exactly what happened here. So the colors are completely fake, and in fact, we can't see infrared light, so we just make up the color. It's up to the designer. Complete fake.
I had read somewhere that the colors are indicative of the chemicals or
Yes.
gases that they're depicting.
Yes, the filters that are available isolate the light from different atoms.
Mm-hmm.
So you get to see what the atoms, or more accurately, atoms with some of their electrons stripped off. Each picture gives you an image of a different ion of a different atom.
So you can compare.
They're all black
different
and white.
But you can compare different
Exactly.
objects and their composition based on that.
Yes, I have
that
a
reflects
wonderful
reality.
undergraduate student who's busy at the moment dividing Hubble images by one another because we think the ratios of the images will be revealing of high densities. Yeah, that's what we do. But it all starts with black and white images.
As a geologist, I find this fascinating. In part, I'm curious about what you're seeing where you're talking about color. Is it got to do with the speed or
No.
the
It just hasn't.
ionic relationship or covalent relationship between material?
You're getting much too complicated. The colors are all inserted by the graphic artist who overlays images in Photoshop. It's that simple.
Then the color is added by the graphic artist,
Yes.
but the graphic artist is seeing particles or seeing
The graphic artist begins with photographic well, we don't use photography film anymore, starting with digital images, just like your cell phone takes,
yeah.
but they're black and white.
How
And
does
they
it
were-
integrate with Boeing reaction series?
Bruce, is anybody else doing this work beside us?
You mean in the universe?
I mean, here on this globe, are we the only country that's doing this kind of
Oh, no.
sophisticated
No,
stuff?
no.
Well, who's doing other stuff, and what are they doing?
Well, when I get an image from Hubble, it stays inaccessible to anybody but me and my collaborators for a year, and then it's wide open. Anybody can get at it. So these data fairly quickly become internationally accessible, and that's purposeful.
But we're the only ones that have sent a telescope out.
Well, Webb is a gigantic collaboration of NASA and the European Space Agency and the Japanese Space Agency.
I was asked by someone who couldn't stay.
Will have to be the last question.
I was asked by someone who couldn't stay to ask you the same question that I had in mind, which like blew me away. If there was someone on one of those dots taking a picture, oh, excuse me, and taking a picture of us,
Yeah.
what would that look like? Would we be able to see the number of Starbucks restaurants in the world or something like that? Is there, if we had greater magnification of the things in that picture,
Yeah.
what would it take, and is it theoretically possible to discern whether there were organisms, animals or plants of any
So
kind?
one of the basic tenets of physical cosmology is that the universe is uniform, absolutely uniform. The same kinds of mix of things that we have around us is the same mix of things that is everywhere in the universe. We have tried many times to disprove that and failed every time. As best we know, any picture taken by any astronomer anywhere in the universe would look, not in detail, but in its essential features, would look the same.
So we have to wait until we get better and better
Yeah.
pictures to test
So,
that.
you know, one question that people ask, we know the universe is expanding. Everywhere we look, things are moving away, not towards, away from us at speeds which increase with their distance. That's called the Hubble law. A lot of people come to the conclusion that we must be at the center of the universe in order to see that pattern. One of the homework problems I give my Astronomy 101 students is a sort of a graphic representation of the universe where you observe the expansion patterns that we know from here, but from elsewhere, a universe in which is expanding in such a way that distant things move apart faster. And I asked them to look at the trends of the speed with distance and see if there's any difference as they go to different galaxies, and the answer is no.
It's very sobering.
Thank you very much, Bruce.
You're welcome. My pleasure.